So the question is, how do we map and monitor subsidence? So who can tell me what subsidence is? Land sinking, yeah? So what is the actual physical attribute of land sinking that we want to measure? Elevation change, okay? How do we measure elevation? Okay, so some good ideas. There's a couple of different ways to map elevation. So go back a step. So we have subsidence, which is land sinking. Land sinking is a change in elevation. To understand the amount of change in elevation, we need to know the elevation to start with and the elevation to finish with, yeah? So we can map elevation in a number of different ways, both in the field and through remote sensing techniques. If we're in the field, it's usually with GPS. If we're looking at using satellites or airborne sensors, we have the main options are radar or LiDAR. Okay, two different types of active sensors. So the first one, looking at synthetic aperture radar and a process that we call interferometry. Okay, so if we look at radar, basically what it's doing is it's sending out a radio wave, and then as it comes back, it looks at the phase shift of a wave. Okay? So in this particular technique, if you imagine the satellite here is sending out this pulse of radio, and if something has shifted, when that pulse goes back to the satellite, the phase of that wave actually comes back slightly different to what it did in the first place. Okay, so if we look at it here, it's hitting the land on this upward bit of the curve, and this time it's in a slightly different location, okay, in that actual wave. All right. And that difference is then associated with the change in elevation, okay, or slip. So this is done a lot to look at water extraction, at volcanoes as they expand and contract, and earthquakes as well as the ground changes. If you guys are using digital elevation models at all in the GIS class, the most common freely used one is the SRTM DEM, which is the Shuttle radar topographic mission that was run probably about 15, maybe even 20 years ago now. And it was using radar technique to map the elevation of the Earth. Using this technique, we need to get two dates. Okay, so before something happens and then afterwards as well. So here's the SRTM. It actually used 2 satellites, and that allowed us to get the first ever highly detailed digital elevation model. Okay, and that's mostly what you guys will use if you're touching any DEMs at all throughout your studies here. So that gives us the basis for any form of 3D mapping over relatively broad areas. And that when it was first available, that was at 120 meter pixel size, but it's higher resolution than that now. It's been reprocessed. So this is an image that gives some information about how land has changed. This is a particular example from New Zealand, using that interferometric example. Okay, so where it's looking at the wave shift from when the pulse of the radar wavelength hits the Earth and then when it comes back. Okay, so it's showing a range of different things in this particular image. All right, the colours that you see actually give an indication of the noise that we can see in an image and where things are maybe not quite so useful. So for example, if you have changes in the land that are not necessarily associated with deformation of the land, so you have a change in vegetation, for example, like what we see here with agricultural fields, this gives us a change of signal, which could be change of elevation, but knowing that particular scene, that's more likely to be related to the change in either moisture or the vegetation that's in those particular fields there. This is a nice example of some processed data using the same technique of the phase shift of radar that shows you the amount of deformation that occurred post-earthquake just off the southwest coast of New Zealand. So if you have a look up here, you can just see a little star, which is where the earthquake occurred. So it was offshore. And this part here is the processed imagery. So the actual scene went out on the water as well, but it's not of use there. But what you can actually see is the level of deformation in the land. The point here closest to the epicenter of the earthquake. Okay, so we had about 15 centimeters of uplift in that particular region of Fiordland in New Zealand there. And then of course as it went further and further away from the epicenter of the earthquake, the less deformation that was seen. Okay, so all the way down to sort of nothing around these areas. This is an example of what you might see coming out of volcano analysis and how a volcano can be shrinking and expanding based on the activity that's happening subsurface. Okay, so any magma movement will actually cause volcanoes to seem like they're pulsing in a way. This same technique can also be used for looking at glacier movement. So again, it's looking just at that shift and can actually measure the not only the distance that something's moving, but then based on the time that's elapsed, that it actually measures the rate of movement of that particular glacier. Okay, so going back to the initial question of how does remote sensing monitor subsidence, that's still a change in what's actually happening on the surface, and it is a form of deformation, if you like. And it's the same sort of thing that we see here with our glaciers. Okay, so some problems that we have with these techniques. So I find radar data really, really difficult to analyse. And if you look at the techniques that we deal with in this class, we look only at optical data, so Landsat, MODIS, WorldView. So that's where my area of interest and expertise is. So for someone who's a remote sensing scientist, you generally deal with one main set of data. So people that deal with radar are like, it's an entirely different discipline. So I know small amounts of it, but I certainly don't know large areas of it because there's so much more involved in that. And then LiDAR is another one as well. So you rarely get people that do the whole spectrum, if you like, of remote sensing. And one of the reasons that I don't get so much into radar is because this is what the imagery looks like, and it's not really pretty. So it's difficult to analyse. You don't get the nice colours, so Alan might be actually quite nice for you in just having the black and white and the different shades of grey. But the patterns are totally different to what you actually see in the visible and near infrared and shortwave infrared imagery as well. So you're getting out different types of information, but it's you need to understand a whole bunch of other science behind that as well. So there's a lot of issues with atmospheric artifacts in the imagery, and also changes can be related to things occurring on the surface of the Earth that actually aren't the changes that you want. So like I said, with vegetation change and regrowth as well. And this method is also good for relatively small movements, but larger shifts can become harder to detect as well, which is kind of counterintuitive really, but that's just due to the wavelength of the radar that you're looking at. So an alternative to radar, and this is usually based on airborne platforms, are LiDAR systems. So radar being radio detection and ranging, LiDAR is light detection and ranging. Okay, so same sort of thing, being an active sensor, it sends out a pulse of energy and it records the amount of time taken for that pulse to come back. So a LiDAR system is usually either green or near infrared. So then the near infrared systems are usually used over land, and green LiDARs are often used for bathymetric mapping. So as you know, the green goes through water more than a near infrared will as well. But essentially it's doing the same sort of thing as the radar in that because it's measuring the amount of time that it takes for that pulse to go down and come back, it can then it can then estimate the elevation of the point where of the land where the beam hit. Okay, so it travels at the speed of light, and then it can work out that distance. So I really like this example of Mount St. Helens, because this shows some high temporal resolution airborne LiDAR data that shows exactly what's happening in the volcano in terms of its movement and change in elevation. Okay, and this is exactly the same sort of thing, looking at deformation, and you could use a similar sort of technique for looking at subsidence as well. So you can really see that in 3 dimensions what's happening there, which is really quite cool.
Is that
That's land, yeah. Yep. So LiDAR is showing elevation, okay? So that you might see textural differences. Oh, that's noise in that one where you see the scattering there. But yeah, this is a digital elevation model.
Is that in a 2-hour clock?
No, they're days. Days, yeah.
That's days.
Yeah, it's over a few months.
That's insane.
September, November.
So, I mean, you know, volcanoes are responsible for building whole new geomorphic features in the landscape and for islands popping up out of the ocean. And that's, you know, it's essentially what you're seeing there. LiDAR is, there is space-based LiDAR, but it's not so heavily used. It's usually an airborne system, and it is really quite expensive to acquire as an airborne system as well. So this is a unique data set in that it's been done repeatedly to really get that time series, which is really neat. So hopefully that's given you guys a bit of an insight into how active sensors can be used to map changes in elevation, which then comes back to the question of subsidence. So you can use exactly these techniques to see what's happening as the land shrinks, as water is taken out.